This unit is about Kirchhoff's voltage law and how it can be used in circuit analysis problems. Kirchhoff's voltage law states that the total voltage around a closed loop is equal to zero. This is a direct outcome of the principle of conservation of energy, and it is an integral part of any circuit analysis problem. Similar to our study of Kirchhoff's current law, I am not yet specifying the nature of the devices in the circuit. We will eventually learn about some of these devices, but the important takeaway here is that the application of either Kirchhoff's current law or Kirchhoff's voltage law does not depend on the nature of these devices. Note, however, that I have assigned a voltage across the terminals of each device. Note as well that the voltage takes the form of a name starting with V and a subscript that differentiates all the voltage drops across each separate device. In other words, each device voltage drop or rise needs to be identified in a unique way. Integral to the definition of the voltage is the assignation of the plus and minus signs, which serve to identify the polarity of the voltage across each device. The plus sign denotes the side of the higher potential and the minus sign the side of the lower potential. Sometimes we have to assume what this is, but we will always consistently use our notation in KVL. This is an important distinction and necessary in order to set up the problem appropriately for the application of KVL. In applying this closed loop theory, is it important where I start? And it is really important that you understand that it is not important where you start. What is necessary is to set a starting point and then follow it all the way around the loop, and you're not done until you end back at the same point. In addition, as you go around the loop, you need to make sure that you record all of the voltage drops and rises that you come up against along the way. So the final equation for this particular setup is Vs minus V1 minus V2 minus V3 is equal to 0. But what we really need to discuss now is how I actually came to this equation. Before we discuss how I came to the final equation, let's discuss being systematic about our approach to solving these problems. First, as in the case of KCL, you need to identify all of your nodes and assign a name to each node. Before we do that, let's talk about our nominal ground. This is a point in your circuit that you will choose as your zero potential node. This is identified through the ground symbol, as you see that symbol with the 3 horizontal lines. And we will use this concept quite a bit later on, but for now we'll just use it as ground. And if we look at the rest of the circuit, we can isolate 3 nodes: node A, node B, and node C. Now, remember that the voltage between 2 points needs to be defined by a plus-minus polarity designation as well as a unique name. In order to make this name unique, as well as definitive, we assign a subscript that corresponds to the nodes across which the voltage is defined. As you will see, the high node is identified first and then the low node is identified. For example, the voltage across the source is equivalent to the voltage between node A and ground. And so I will denote it as V subscript A. Note that in the case of a node voltage, in other words, in a case where I'm identifying the voltage between a node and ground, I only use one letter in the subscript. And this, when I only have one letter in the subscript, then I am by definition defining a node voltage. In other words, the voltage between any point in my circuit and the ground in my circuit. In the case where the voltage exists between 2 nodes, none of which are the ground node, we use a subscript that identifies each of these nodes. In addition, the order of the nodes has to be from high to low. So because I put the plus on the A side and the minus on the B side, this voltage between A and B is going to be V subscript AB. If I had decided to put the plus on the B side and the minus on the A side, I would then have named that voltage VBA. So let's look at our smiley face again. The voltage between node B and C is likewise VBC, and the voltage between C and ground is VC. And you note here that we have two node voltages identified in this circuit. So if I look again at my smiley face starting from ground, and it is usually easier to start from ground if it exists in a particular loop, I move counterclockwise until I arrive to my first component, which happens to be the source, and I arrive at the negative node of VA. As I continue this looping around, I end up at the positive node, and that's the other side of my component, and this is a voltage rise. In other words, as I go around a loop and I hit a component, if I hit the minus side first and then the plus, then I am recording a voltage rise. So I will write down that voltage rise as VA in my equation. All right, so I have VA. Now I'm moving from node A to node B, positive node first, negative node next. This is a voltage drop. And so that means that I've got VA minus VAB. If I go from B to C, that's another drop. And so that's VA minus VAB minus VBC. And then that's another voltage drop, VA minus VAB minus VBC minus VC. I make sure that I've finished my loop and I have no more components. And so I end with VA minus VAB minus VBC minus VC is equal to 0. And that is my final KVL equation for this loop. Now, you will not have access to any sort of animation. So in your case, you will actually draw a loop, that circular arrow. That arrow has to show in which direction you are applying KVL. You will name the loop, loop 1, because that helps you later on in your solution to identify which loop you are working on. It helps me grade your solution. And for the specific case we are working on, the loop is identified as going clockwise, and KVL is written as VA minus VAB minus VBC minus VC is equal to 0. That's the exact situation we had before. If I had decided to go in the other direction, then my loop 1 equation would have been VC plus VBC plus VAB minus VA is equal to 0. And I think it's important that you prove to yourselves that this does not change the KVL equation. And this is a very important thing to know. As long as you are consistent and as long as you are systematic, your equations should always give you consistent results. So how can I use this? I'm going back to my original loop. If you know 3 of the voltages in this particular problem, you can solve for the 4th. So say you are given VA equals 10 volts, VAB equals 5 volts, VC equals 2 volts. You solve VA minus VAB minus VBC minus VC equals 0 for VBC. And you substitute and you calculate VBC equals 3 volts.